To our third speaker for the session, Professor Kemal Celik. He is Associate Professor of Civil Engineering at New York, Abu Dhabi, and he also Director of the Advanced Materials and Building Efficiency Research Laboratory. He has a PhD from University of California, Berkeley, and I'm not sure exactly when did you mention New York, Abu Dhabi, but the floor is yours. I mean, listening to you is much more important. Thank you.
Good morning, everyone. It is a privilege and pleasure to be here today, standing before you today. I also know that I am standing between you and then coffee break with delicious treats, so I'll try to make it engaging. In the meantime, I promise I'm not going to show you too many mathematical equations or chemical formulas. So, previous speakers already mentioned about sustainability, global warming issues. Also yesterday, Mr. John talked about concrete sustainability. That was a perfect seg into our next conversation or next talk about magnesium-based cement produced from desalination brine. But before doing so, for the ones who are not familiar with the MIU Abu Dhabi is a relatively new institution, and we welcome our first students in 2010. And it is a smaller version of United Arab Emirates. As His Highness mentioned the day before, there are 200 countries represented in the country. At MIU Abu Dhabi, we have more than 120 countries represented. And it's a research-based university. We have 3 campuses, one in New York, and of course, the other one in Shanghai. And I am based in Abu Dhabi. Here, I'm representing this diverse group and great individuals, brilliant researchers who made of Amber Lab, Advanced Materials and Building Efficiency Research Laboratory, established in 2017. And I will be giving some snapshots of our ongoing projects. And there will be some subliminal slides as well, because I'm in the science community. I'm sure I don't need to go too much detail. Some of the techniques that we use, so I'll keep it short, that slides as well. So the research scope of Amber Lab is, or research horizon of the Amber Lab is large, starting from the nano-characterization, material characterization in the nanoscales, all the way to the engineering scales or large-scale application. Today, I'll be mostly talking about magnesium-based cement. It is an alternative cement to the traditional or Portland cement that absorbs CO2 during the strength gain mechanisms. And as we all know that in the middle of the 21st century, the population will increase from 8 billion to 9.7 billion, and most of the population will be living in the urban areas. And among those, they will be living in the coastal area. And of course, it's a good news as engineers, practitioners, developers, or contractors. Architects, we are going to build lots of civil infrastructure. Also, we can translate into academic perspective. We will have a chance to educate next generations of engineers, architects. And if we look into the research perspective, we will have a chance to do cutting-edge research to address sustainability and resiliency issues, and reconsider our current practices as whole community, and enhance the properties of our infrastructure. It's also good to know that 40% of the greenhouse gas emissions comes from the buildings. And both UAE and United States has a large room to improve in that scheme and increase energy efficiency and reduce the global greenhouse gas emissions. Studies show that thermal insulation of the buildings play important role in the energy efficiency of the building. And to build our structures, we use different materials like steel, wood, ceramics, plastic, and of course concrete. And concrete is the most widely used human-made material after water. And then it has a carbon footprint match. And projections shows that demand for cement will increase by the year significantly, and our goal is to reduce this CO2 emissions associated with the cement production. On top of these challenges, arid regions like Middle East and North Africa has water scarcity issues, and to narrow the gap between water supply and demand, desalination plants play important role, and most of the desalination plants, almost half of the desalination plants are located in the Middle East and North Africa regions. Of course, desalination isn't without consequences. After water is desalinated, there is an accumulated highly saline or hypersaline water, and current practice is discharging back this saline water into the Gulf. And the Gulf that we have here is one of the hottest and saltiest body in the world, and discharging back this salty water is not environmentally friendly approach, and that's why we like to deal with these pressing issues. So the challenges we have is substantial carbon footprint of the cement industry or construction industry, also increased discharge of the desalination reject brine, and then opportunities will be using this brine and produce environmentally friendly cementitious material like magnesium-based cement. And then after processing, we can reduce the total dissolved solid in this hypersaline water and discharge back to the sea safely. Of course, it requires multi-scale approach to address all these scientific challenges, starting from material characterization. And today I will be mostly talking about these 4 scales and give some snapshots of our projects. The first project that I'd like to highlight is using reject brine or brine of the desalination process and produce as a construction materials. So magnesium-based cement is not new. Magnesium-based cement is produced from magnesium carbonate in a dry route, but of course, in relatively lower temperature for the calcination process. It's around 800 degrees Celsius with respect to 1400 degrees Celsius that is needed for the calcination of Portland cement clinker. And this decomposition of magnesium carbonate into magnesium oxide and CO2, the one that we don't want it, because at the end we are producing CO2 and emitting CO2 in the atmosphere. So the new route that we'd like to work on, or we are working on, is the using waste brine and use cost-efficient chemical agent and produce brucite. Brucite is magnesium hydroxide, and then the source of alkaline that we are using is also can be produced from this effluent of this reject brine or other sustainable sourcing, and that create a closed loop and total recyclability. I promise I don't want to show so many equations, etc. But these are the important ones. Okay, magnesium hydroxide is produced after desalination brine is treated, and then to gain the strength, it needs to absorb CO2. And the minerals that are produced after this carbonation process, nesquanite, dipenjate, hydromagnetite, and arsenite, these are the minerals that have different strength and different surface area. And of course, to precipitate magnesium hydroxide, it requires some optimization process. We vary the calcium oxide amount and then find this sweet spot with respect to precipitated powders versus brucite yield and optimize our process. And after this optimization, we did ICP-OES to measure the cation in the system, and the recovery is around 96%. 96% of the magnesium is recovered after this process. We also utilize different alkaline like sodium hydroxide ethanol amine or ammonium hydroxide along with calcium oxide. But I didn't add this slide, those slides in my presentation. We also did life cycle analysis. So most of the CO2 emissions or greenhouse gas emissions comes from the production of this alkaline. And calcium oxide is most environmentally friendly approach to process this reject brine. The primary phase in this precipitated phase with different alkaline, as mentioned, are brucite, and there are some trace amount of calcite or aragonite. Most likely it is because of the initial pH of the solution that use it. And once we have this brucite, we need to cure it in an accelerated carbonation condition to increase the strain gain process. So the one in the cured in the air, it reached around 10 megapascal, but once we accelerated the carbonation process with 20% CO2 and 80% relative humidity at 30 degrees Celsius, the strength development is significant, and it's around fourfold with respect to ambient curing condition. And 30 megapascal is sufficient for most of the structural or construction application. And in another project funded by NSF, we want to maneuver nucleation, growth, and phase transformation mechanisms with in situ visualization of the magnesium carbonate through nucleation mechanisms. This is an ongoing project, so this is the subliminal slides that I am not going to go too much details, but we use the transmission electron microscopy similar to the light microscopy, but instead we use electron gun. And then we were able to look into the morphology, diffraction pattern, and chemistry or EDS maps. And the special instrument that we use is in situ carbonation chamber in this instrument. And in this chamber, we are able to vary the pressure, flow rate, temperature, also gas mixtures, and use tiny sample holder assembled into TEM machine. And using the silicon carbide and silicon nitride chip, we add our samples and look and assemble into TEM and look into the carbonation and hydration mechanisms in real time. So after around 20 minutes, we are able to see some round shape here going around, and then after around 1 hour, there's a edge breaking out and start of nucleation, and then growth on these edges. And after around 2 hours, we see small size, nano-size particles are forming in the structure, in the microstructure. And we suspect that it is an amorphous magnesium carbonate because there is no clear pattern in the diffraction pattern. And then this kind of techniques also can be useful for getting other real-time monitoring for this kind of fractal growth. And it is a very unique instrument that we are able to access at core technology platform at NYU Abu Dhabi. So another project that I want to highlight is using supercritical CO2 to accelerate the carbonation process. So as you are familiar, most likely supercritical CO2, it has a low viscosity and can penetrate into the materials deeper and deeper. And what we need is just to increase the temperature around 31 degrees Celsius, and then pressure around 7.5 megapascal, and then see how the phase transformation and CO2 sequestration capability in the matrix. So we have 3 samples. One is the magnesium cement, it's cured in the air, and the other one is accelerated carbonation chamber that I mentioned, and the third one is the supercritical CO2, and we compare the result, and there's a comprehensive testing program that I'm not going to show all of them, but the most important one, the Raman spectroscopy show us the main phases, as mentioned, is brucite, but we are able to see the peak for this nesquinite and hydromagnesite. And the one that we are seeing here, hydromagnesite at 28 days of curing in accelerated carbonation condition. But if we use supercritical CO2, hydromagnesite peak is disappeared, and mostly we have nesquinite phase. And we also observe this in SEM. Here we see magnesium cement cured in the air condition. Mostly we see the flake type magnesium hydroxide. There is not much carbonation, but if we accelerate the carbonation at curing chamber, nesquinite and hydromagnesite phases are appeared. For the supercritical CO2, just after 1 hour, 2 hours, and 4 hours, we see the needle-like shape of which are the nesquinite phases, and then after 4 hours, all these nesquinite phases are kind of fused, and there is no clear pattern of the crystals or minerals. So, as an engineer, we have to look at how strong these materials. After curing, as I mentioned previously, we have significant strength gain in the magnesium-based cement, but we need to wait around 3 days, 7 days to gain this strength. And for the precast concrete industry, we need to accelerate the cycle of the production in an hour, for example. So in this case, supercritical condition will be much more useful. In 4 hours, for example, we are reaching around 40 megapascal and slightly above the strength of the accelerated carbonation condition, and the carbon sequestration factor is around 30 to 34%. Here we see another version of this mechanical strength development with respect to water to binder ratio. At 14 days, the one is curing the environmental chamber reach around 30 megapascal, and the one in the cured and the supercritical reactor reach much higher strength. And in this region, 3D printing is also another hot topic, and we'd like to see how this material is 3D printable and how adding cyanosphere is a byproduct of the coal combustion power plant, will be useful to improve the thermal insulation of this structure and produce lightweight composite. So we look at 3D printability of this magnesium-based cement, adding 20% cyanosphere and some PCE-based chemical admixtures, and we are able to 3D print this material with intriguing shape, and we also compare the one that is printed versus cast sample and curing this accelerated carbonation condition. And as I mentioned, cyanosphere is a byproduct of the coal combustion power plant. These are hollow, inert material, and here we see some of them here, and then some of them are pulled out after testing, and we are able to see also hydromagnesite minerals in the microstructure. And we look at the thermal conductivity. As expected, thermal conductivity is decreased by increasing the cyanosphere, this porous material, and we compare the result with cast and printed version. Since 3D printing also increased the porosity in the structure, 3D printed structure has a lower thermal conductivity. And in terms of strength development, 3D printed structure has larger strength. If you look at this 20% cyanosphere replacement, it is because of the carbonation process. 3D printing provides larger surface area, more porous structure, and then carbonation is increased during this process. And we can safely say that 3D printing and carbonation will be a good option in magnesium-based cement. And in a continuation of this NSF project, we'd like to see if we can reinforce this engineered magnesium-based cement with synthetic fibers. And ECC or engineered cementitious composites are a relatively newer group of ultra high performance concrete, and as you know, concrete is brittle material in tension and flexural. It can break easily, but ECC or engineered cementitious composite is also called bendable concrete. Through fibers, we can increase the strain capacity. The goal is to increase the strength of this bridging matrix and get higher fiber bridging strength than the matrix strength by itself, and then dissipate or absorb this energy through laminar or flat cracks, and energy dissipation needs to be appeared to have this bendable concrete. So there is a tedious micromechanical modeling that I'm not going to get into too much details, but our goal is increase the energy dissipation through fiber addition, and then increase the bendability or strain capacity of the concrete. So the parameters that we can tailor is the fibers itself, fiber matrix interface, and then matrix. And there are different parameters within these three main parameters. And we can test this fiber matrix interface with a single fiber in our facility. Of course, also get the bulk material properties through flexural test and tension test. So by tailoring this mixed design, we are able to produce some ECC or magnesium-based engineered cementitious composite and produce some cube samples, prisms, and dog bone samples, and then test them in this tension test and do some digital image correlation to see how these materials are behave under loading. So again, this is an ongoing work. I'm just giving you a heads up. There, we are able to see the energy dissipation through cracks, but our goal is to increase these cracks throughout the matrix. And then this is the test that we have done for the 4-point bending test. Again, once it is loaded, we can see the cracks, also stress and strain development. And what we'd like to see, the red color changes distributed towards the bulk faces. So, to wrap up my talk, I'd like to show you a short video and brings what we have discussed to the life. We are attending a competition, a UAE-based competition. Actually, it is an international competition, but organized by the Environmental Agency of Abu Dhabi. And currently, we are in the last phase of this competition. We have been dealing with 4,000 liters of brine per day, daily, at this stage of the competition. But this video was prepared for the previous stage, just showing the 300 liters of brine. I hope it will work.
The Middle East and North Africa region accounts for 70.3% of global brine produced from the desalination process. Direct disposal of this brine to the sea has adverse effects on marine life. Meanwhile, several industries, including construction industry, evolves to employ low carbon footprint materials and contribute to net zero carbon dioxide goals. With these motivations, Amber Lab at NYU Abu Dhabi came up with Macaulay, a 3-stage process to recover magnesium hydroxide, calcium oxalate, and lithium carbonate from reject brine for construction and energy applications. This technology combines 3 stages involving chemical precipitation for the recovery of these minerals. In stage 1, we employ a simple precipitation process to synthesize brucite from reject brine. In the synthetic procedure, Calcium oxide, a cost-efficient precipitation agent, is mixed with deionized water, which is then added to 15 liters of brine. The solution is stirred for 1 hour. The milky solution is then centrifuged to separate the powders and calcium-rich brine, directed to stage 2. Depending on the purity required for brucite, the wet powders can be washed in one or several centrifugation cycles using deionized water and achieve up to 94% purity. The wet powders are then transferred to heat in an oven at 100 degrees Celsius to obtain anhydrous brucite. In stage 2, a similar precipitation process can also be utilized to recover calcium ions in the form of calcium oxalate, a valuable mineral that uses oxalitic acid as a cost-efficient precipitation agent. This process is similar to stage 1, where oxalitic acid could be added directly to calcium-rich brine from stage 1 to synthesize calcium oxalate powders within 1 hour of reaction time. In stage 3, lithium carbonate could be recovered by a combination of evaporation and precipitation procedures from the effluent brine of stage 2. The evaporation process is required to increase the lithium content in the brine. Sodium carbonate could be then used to precipitate lithium carbonate from the high lithium content brine at reaction temperatures above 80 degrees Celsius. Our prototype successfully demonstrates the technology for producing brucite and calcium oxalate. The precipitation stages are capable of producing 300 liters of brine per day and recovering up to 99% of magnesium in the form of brucite, with a yield of 10.4 to 10.9 grams per liter. Calcium oxalate can be synthesized with a yield of 11.8 grams per liter. There is a huge potential for these recovered materials, while magnesium-based cement is a sustainable alternative to ordinary Portland cement. Calcium oxalate could be used for potential applications in the ceramic industry to produce ceramic glaze. Lithium carbonate is also an important industrial chemical as precursor to the compounds used in lithium-ion batteries. Our brucite production process reports around 0.78 kilograms of carbon dioxide emissions per kilogram of brucite. What is unique about the precipitated brucite is that it sequesters carbon dioxide for strength gain. Its carbon dioxide absorption capacity can reach up to 35% of brucite weight. Compacted pellets of the brucite could be carbonated to achieve strength in the range of 26 to 30 megapascal for construction applications. Macaulay aims to expand the technology to the sea with its endless supply of resources. At Amber Lab NYU Abu Dhabi, we envision a world where future generations live in harmony with the environment.
And I want to thank our sponsors for their trust and financial support, and I also would like to thank your attention. Thank you.
Thank you, Kemal, for the nice presentation. Now we open the floor for questions. Please.
Thank you very much. Can you clarify the role of supercritical CO2 and exactly how the process works? Is it just simply large amounts of CO2 being available in the composite?
Yeah. Why we use supercritical CO2? The carbonation usually occurs on the exterior surface and then block the penetration of the CO2 into the inner area. And then through supercritical CO2, it can penetrate in the deeper region of the matrix and then increase the carbonation within the matrix, inner side. And then, of course, it happens very quickly. Instead of waiting in a few days, the process is completed in a few hours. And what we need is a little bit pressure and then also increase the temperature around 32 degrees Celsius. Yeah, my pleasure.
Yeah, thank you very much. It's a very interesting project, this. With making magnesium from brines is obviously attractive because brucite as a natural mineral is quite rare, and also magnesite's quite rare as well. But how scalable is this process, though, if you wanted to use it for making a magnesium-based concrete?
Yeah, that's a good question. As you said, a magnesium carbonate deposit is geographically limited, and mostly it's based in the China or Russia and North Korea. And this process can be scalable. Right now, we are dealing with 4,000 liters of brine. But if we have a continuous stream of this brine itself, we can make a continuous precipitation. What we need, larger tankers. Also, of course, we need a process engineer to increase the steering process and then make it more efficient. And I haven't shown this last prototype, but we are showing we are demonstrating that this technology can be scaled up, and deal with 25,000 cubic meters of brine per day. So this is the process that we aim, and this is the goal of the competition that we are attending right now.
And if I could ask another question, sure. Have you thought of using the magnesium hydroxide, the brucite that you make, to capture CO2 out of flue gases?
Exactly. So this is the goal. Our goal is to establish our pilot plant beside or next to the flue gas or CO2 emitter industry, and use it, because at the end, construction materials doesn't need to be very pure. So all this impurity can be accommodated in the structure, like calcium or other impurities, and then it will be an ideal solution, because we need a CO2 to absorb directly from either industry or through the tanks.
Yeah, thanks very much.
Sure.
Any other questions? Yes.
Okay, thank you, sir, for this presentation. So I have two questions. So first one is, what is the volume fraction of the fiber that you used in the fiber-based composite? And the second one is that in your slide, you have seen that one is a 3D printed composite.
Right.
So what was the MFI of that final solution or mixture? That
What
you 3D print? MFI, melt flow index or melt flow rate of the final solution that you 3D printed. Because MFI is basically 3D printed depend on the MFI. If your MFI is very low, that means molecular very high, right? Then it cannot be printable. So what was your MFI?
So the first question that you ask is about the volume percent of the fibers. It's 2% with respect to total volume. For the 3D printing, I couldn't get exactly what you asked, but we use some PCE also. Yeah, but I couldn't get the term that you talk about for 3D printing.
Yeah, it is called melt flow rate. Because for 3D printing you need some flowability, right?
Yeah, exactly.
Okay, so there is some rate and range of the rate above which it cannot be printable. So that's what I want to know. You calculate the rate?
Actually, this is a part of my PhD student, so I don't have the exact value in this. But we look at the rheology and then flowability. And the green time for this 3D printing is around 40 to 60 minutes, but I don't have the exact number on my top of my head.
Maybe I can help you with this,
yeah.
Because in 3D printing, what you're talking about is related to polymers, or maybe like the 3D printing of metals and alloys. But in this case, it's mainly aqueous. We are talking about slurries, so you care more about the consistency of the flow and the rheology and so on, much more than you do not have melting basically. But I have a question, if you don't mind.
Yeah, sure.
Also related to the fibers, have you thought about the interface between the fibers and the composition in terms of like chemical interaction, or otherwise you're going to have the fiber debonding or removal of the concrete? Is it one of the parameters that you studied?
Exactly. This is what we are working on. I mean, we are using the single fiber, look at the interface between matrix and the fiber. And the fiber that we use, PVA, polyvinyl alcohol-based fibers produced in Japan. And this is the common fiber specifically produced for this ECC structure. Victor Lee from University of Michigan, he is the pioneering professor researcher in this field, and that fiber is specifically produced for the ECC matrix with this surface coating and increase the interaction between matrix and fibers.
One more question, if you don't mind. It's related to Tony's comment about the commercialization and maybe like industrialization, pilot scaling up. Is it in your plan that you can have your pilot scale very close to the desalination where you can take the brine right away to your factory?
Exactly. I mean, this is the ideal case because we need a supply of the brine. Also, we need a supply of CO2 emissions, and both of them are available in the desalination plant. And currently, we are in touch with the water and energy companies based in Abu Dhabi. And the company is the one supplying all of the brine into our lab. But if we can move there beside their facilities, that will be ideal one. Yes.
Thank you so much. Any other questions? Yes.
Thank you. I have a question. So, while pelletization, do you have any binder? You have used any binders to provide more strength?
Binder?
Do you use any binder to provide more strength to the pellet?
So binder is by itself, magnesium hydroxide is the binder. These are hydration mechanisms that create binding mechanisms. Also, in addition, we have carbonation on it. Yeah.
Okay. And the final question is, so what is the optimum pressure you have adopted in this project?
Of ultimate?
Optimum pressure.
Pressure. I mean, for supercritical CO2, we just use 7.5 megapascal. But we can reduce it based on the industry's need. We don't need to increase the pressure that much. And there are large-scale pressure or autoclave systems that can be utilized for the precast industry.
Yeah, it's a crucial role to sustainability of the bottom.
Exactly, it's sustainability and also the strength and then circle of the production. It needs to be increased for this precast industry, especially within this region.
Okay, thank you.
Okay, let's thank the speaker again. And that marks the end of our morning session. I think Tony has comments.